Welcome to Lecture 9, Introduction to Inference for ECHO 111 Quantitative Methods. In previous lectures, we covered probability, definition of probability, measurement of probability. In last lecture, we talked about probability distributions. We talked about normal distribution, binomial distribution, distribution of a sample mean. Today, we will cover the following topics: estimating with confidence, building confidence intervals, and tests of significance. To get an idea about the applications of what you are going to learn today, here is some extracts from the Wall Street Journal article from the 21st of January 2011, Taco Bell, the beef, it's real. In this article, they talk about a recent scandal that hit Taco Bell company regarding the amount of beef in their tacos. Particularly, recent survey had found that taco mixture was only 88% beef. The problem was that people were expecting a larger proportion of the taco mixture to be beef. In cases like this, how can a company prove that its product has 88% or more beef? How can you make claims about the ingredients of food products? How do you make inference? There are two main methods by which we can use sample data to make inference conclusions about a population parameter. The first one is constructing what's called confidence intervals, that is, give a range of values for the population parameter. Another one is to execute tests of significance, by which we assess whether a claim or a hypothesis about the population parameter is true or false. In order to be able to make inference, we must have sample data which is produced either by a random sample or a randomized experiment. Particularly, we want data that is not biased. Today, we'll be addressing cases where we make inference about the mean when we have a perfect simple random sample, here SRS, from the population of interest. Basically, we have a sample which is not biased, and that includes having no problem of non-responses or any other practical difficulty. We also don't know the population mean, but we do know, in this case, the population standard deviation sigma. While these conditions are unrealistic, they do provide a base case to which other situations can be compared to. Let us start with an example. Suppose that you take a simple random sample, SRS, of 16 observations from a normal population with mean mu unknown and a standard deviation of 20. The sample mean of these 16 values is 240.79. The objective of a confidence interval is to give some information about an interval in which the population mean mu, the population parameter mu, will lie. So in essence, the question we are trying to understand is how close to 240.79, the sample mean, is the population mean mu likely to be. The problem comes from different samples from the same population giving different sample means. So in order to answer this question, we must first answer the following question. How would the sample mean x bar vary if we took many simple random samples, SRS, of size 16 from the population? The answer to this question depends on three important characteristics of population distribution. Depends on the shape of the population distribution, if it is symmetric or not, skewed to the right or skewed to the left. In this case, the population distribution is normal, so the sampling distribution of x bar will also be normal. However, we know from the central limit theorem, even if the population distribution is not normal, the sampling distribution of x bar will be normal. Second, it depends on where the center is. We know from the previous lecture that x bar is an unbiased estimator of the population mean mu, regardless of the distribution of the population. The last property is the spread. The standard deviation of x bar will depend on the standard deviation of the population and the sample size. In particular, it will be sigma, the standard deviation of population, divided by the square root of the population, the sample size, in this case 16. So in this case, the sample standard deviation is 5. Here is a graphical representation of the previous slides. As you can see, the population is centered around mu and has a standard deviation of 20. We take a sample of size 16 and we get an average of 240.79, but different samples will give you different values for the average. Therefore, this will give a distribution for the sample average, and this distribution will be centered around mu, the population average, but will have a smaller standard deviation of sigma divided by the square root of n. From the central limit theorem, we know that the sample average will follow a normal distribution with mean mu and standard deviation 5. Furthermore, there is a rule called 68, 95, 99.5. This specifies how many observations are 1 standard deviation away from the average, 2 standard deviations away from the average, and 3 standard deviations away from the average. So this rule basically is saying that 95% of all samples of size 16, the sample mean will be within 2 standard deviations of mu. Because the sample mean is an unbiased estimator of the population parameter mu, the population mean, then saying that the sample mean is within 10 points of mu is the same as saying that mu is within 10 points of the sample mean. Let's say you take 100 samples of size 16, and for each of these samples, around the sample mean, you construct an interval, which is 10 points below and 10 points above the sample mean. 95 of these 100 intervals will have within it the true population parameter mu, the population mean. The interval that we just constructed is called the 95% confidence interval for mu. Basically, the 95% confidence interval refers to how often it captures the true parameter value. 95 of these intervals will have the true parameter value, the true parameter mu, the population average within it. So here's a figure that explains exactly what I'm saying. So we're saying that if we were to take several samples of each one of size 16, 90% of these samples would have the true parameter value of mu within it. So as you see in the graph, almost all of these samples, when you construct a confidence interval, the true parameter mu lies within it, except for one. So here's the conclusion. To say that we are 95% confident is basically shorthand for 95% of all possible samples from this population will result in an interval that captures the unknown parameter. So in constructing a level C confidence interval for a parameter, we basically need to do two things. We need to build the interval itself, which means we have an estimate and we have a margin of error, and we need to decide what will be the confidence level C that we want to use. In statistics, the most commonly used confidence levels are 90%, 95%, and 99%. We want to make it at least larger than 90%. The most commonly used is 95%. So in our example, when we had the sample mean of 240.79, if we will want to calculate the 95% confidence interval for mu, the population mean, then we will use the following formula. We get the estimate of the sample mean, which is an unbiased estimate of the parameter mu, and then we would add and subtract to get the lower bound, subtract, add to get the upper bound of the interval, the critical value times the standard deviation of the margin. And this is what defines the margin of error. So the critical value comes from, we know that the sample mean is normally distributed, so the critical value, if we're looking for the area under a normal distribution that captures 95% of the observations, the critical value will come from a standard normal distribution, will be 1.96 by the standard deviation of the distribution of the sample mean, which in this case is the standard deviation of the population, 20, divided by the square root of n, the sample size, in which case is 16. So we're saying that, remember, the standard normal distribution gives you how many standard deviations you are away from the mean, and multiply by the size of the standard deviation in this distribution, meaning in the distribution of the sample mean, which in this case is 20 divided by the square root of 16, population average divided by the square root of the sample size, we will get the margin of error, which in this case is 9.8. Subtracting and adding this margin of error to our sample mean will give us the lower bound 230.99 and upper bound 250.59 to our confidence interval. Summarizing our previous slides, suppose that we want to construct a confidence interval, then we would start by choosing a simple random sample of size n from a population having a known mean mu and known standard deviation sigma. The margin of error for a level C confidence interval for mu is z star times sigma divided by the square root of n, where z star is the value on the standard normal curve with area C between the critical point minus z star and z star. The level C confidence interval for mu is then the sample average x plus or minus the margin of error m. The interval is exact when the population distribution is normal and is approximately correct when n is large in other cases by the central limit theorem. Here is an illustration of what we mean by area C for the confidence level. So you would have 1 minus C divided by 2 to your left, and you would have area 1 minus C divided by 2 to the right of the central area centered around the mean, in this case 0, from a standard normal distribution. And the critical values minus z star and plus z star are noted in the graph. We can get the z values from a standard normal distribution table to construct the confidence interval. However, usually most confidence intervals will have a confidence level of 90%, 95% or 99%. So for the 90% confidence level, Z star should be 1.645. For the 95% confidence level, Z star should be 1.96. And for the 99% confidence level, Z star is equal to 2.326. You do not need to memorize these numbers as a standard normal distribution table will be provided in your final exam. Notice the relationship between the confidence level and the margin of error. The higher the confidence level C implies a larger margin of error M, thus less precision in our estimates. The lower confidence level C produces a smaller margin of error, thus better precision in our estimates. Now please complete the following multiple choice questions. The correct answer is the confidence interval between 239.28 and 266.72. Here, the sample mean is 253, the standard deviation in the population is 70, and the sample size is 100. For a 95 confidence level, the critical value from the standard normal distribution is 1.96, and you just need to plug this information into the formula sample mean plus or minus the critical value from the standard normal distribution times sigma divided by the square root of n. The correct answer is the confidence interval between 5.64 and 6.16. The same as before. Here the sample mean is 5.9, the standard deviation of the population is 1.2, and the sample size is 90. For 95 confidence level, the critical value from the standard normal distribution, Z, is equal to 1.96. And you just put this information into the formula, sample mean plus or minus, critical value from the standard normal distribution times sigma divided by the square root of n. Basically, 5.9 plus or minus 1.96 times 1.2 divided by the square root of 80. The correct answer is the confidence interval between 7.71 and 8.29. In this case, the sample mean is 8, the population standard deviation is 3.6, and the sample size is 576. For 95% confidence level, the critical value from the standard normal distribution, Z, is equal to 1.96. And you just use this information in the formula given, which is the sample mean plus or minus the critical value from the standard normal distribution times sigma divided by the square root of n, which in this case is 8 plus or minus 1.96 times 3.6 divided by the square root of 576. The correct answer is the confidence interval between 7.61 and 8.38. Here we have the same exercise as before. The only difference is that the confidence level is higher. So for the 99% confidence level, the value from the standard normal distribution is 2.58, rounded. So we can, if we plug that into this formula, what we get is a confidence interval which is wider. The correct answer is the confidence interval between 7.75 and 8.25. Here we have the same setting as before. The only difference is now you're looking for a 90% confidence interval. So the critical value from the standard normal distribution is now 1.645. If you plug this into the formula, what you get is a confidence interval which is shorter in width. Let us now look at the relationship between confidence level and the margin of error. As we explained so far, while constructing a confidence interval, a person chooses the confidence level, and that will determine your margin of error. The larger the confidence level, the larger the margin of error. However, we would like actually to have a case where we can have high confidence, a large confidence level, and a small margin of error. This is because high confidence will give us always the correct answer, and a small margin of error implies that we have a correct small estimate for the parameter, the population parameter. So how do we achieve these two goals, high confidence and small margin of error? Well, the high confidence you can set, but it will determine the margin of error. Is there anything we can do to reduce the margin of error given a certain confidence level? Well, the margin of error, as we explained before, depends on Z star, the critical value from the standard normal distribution, and that is determined by the confidence level. It's also determined by the standard deviation in the population, and this is given. And finally, it depends also on the sample size n. The larger the sample size, the smaller the margin of error. In this slide, you can see the relationship between the sample size and the standard error of the distribution of the sample mean. The larger the sample size, the smaller the standard error of the sample mean. So if we want to reduce the margin of error, we can do so by increasing the number of observations in our sample, the sample size. We can do also something more interesting. Suppose that we have in mind a specific margin of error, specified, for instance, by government regulations for drugs or some manufacturing spec. You can use the relationship between the margin of error and the sample size to determine what is the sample size that you need. Basically, if you are given a margin of error, you can use that to calculate how big your sample needs to be in order to achieve a confidence interval that gets this small margin of error for a given confidence level. So consider this example. Suppose that we are looking at the density of bacteria in a solution. The measurement equipment has a standard deviation of sigma equals to 1 times 10 to the power 6 bacteria per milliliter fluid. How many measurements should you make to obtain a margin of error of at least 0.5 times 10 to the power 6 bacteria for a given milliliter with a confidence level of 95%? So you use the formula that we just presented. For a 95% confidence interval, Z star, the critical value from the standard normal distribution, is 1.96. Therefore, what you have is the sample size must be 1.96 times the standard deviation of the population, 1 times 10 to the power 6, divided by the margin of error that you're looking for, 0.5 times 10 to the power 6. This 10 to the power 6 cancels out. So you get 1.96 times 1 divided by 2 and get this value squared. So the solution in this case, the number that you get in this formula is 15.36. If you had 15 measurements, that would not be enough to achieve this margin of error. Therefore, you always round the number that you're given up. So you need at least 16 measurements. You need a sample size of 16 in order to achieve a margin of error which is at most, meaning smaller or equal to 0.5 times 10 to the power 6. Now try the following multiple choice questions. The correct answer is 2092. Here, the margin of error is 150 and the population standard deviation is given at 3500. For a 95% confidence level, the value from the standard normal distribution Z is equal to 1.96. And you just introduce this information into the formula that I gave before. So N should be equal to the critical value z times the standard deviation sigma divided by the margin of error m. All of this squared. And you should round up your result upwards. The correct answer is 4,706. The difference between this exercise and the previous one is that you have reduced the margin of error. As a result, your sample size has increased substantially. And to calculate this sample size, you use the same formula as before. You use the critical value from the standard normal distribution, 1.96. You multiply that by the standard deviation from the population, which is given at 3,500, and you divide by the new margin of error, 100. And all of this is squared. And you round up your result. The correct answer is 3,315. In this case, the difference with the previous exercise is that you have decreased the confidence level, and as a result, the sample size is smaller. So, in order to find the sample size, you do as the same as before. You get the critical value from the standard normal distribution for the 90% confidence level, that is 1.645. You multiply that by the standard deviation from the population, which is given at 3,500, and you divide by the margin of error that you're looking for, which is 100. The result is then squared, and you round up your result. The correct answer is 6,628. The difference between this exercise and the previous two is that you have increased the confidence level, which is now 99%, and as a result, the sample size required is substantially larger. Again, to calculate the sample size, you do the same as before. You get the critical value from the standard normal distribution, and for 99% confidence level, that is 2.58. You multiply it by the standard deviation from the population, 3,500, and you divide by the margin of error, 100. The result from this equation is then squared, and that gives you the sample size, which you have to round up. Here are some final considerations regarding confidence intervals. Notice that the data needs to come from a simple random sample from the population. This is not the correct formula if you are using different sampling designs. Furthermore, inference, meaning the construction of this confidence interval, cannot rescue badly produced data. Meaning if your data is biased, for instance if you use quota sampling, then your results will not be correct. Confidence intervals are not resistant to outliers, and if the sample size is small and the population not normal, the true confidence level will be different from C. The standard deviation sigma of the population must be known, and the margin of error in a confidence interval covers only random sampling errors. Let us now move on to the final section of this lecture. In particular, let's now talk of tests of significance. So, confidence intervals we were using to get an estimate of a population parameter, the population mean. For test of significance, we want to know if there's evidence to support a certain claim, hypothesis, concerning a population parameter. In most cases, it will be the population mean. First, some definitions. So, a significance test, or test of significance, is a formal procedure for comparing observed data with the claim, also known as a hypothesis. The claim, or the hypothesis, is a statement about a parameter, like the population proportion P or the population mean mu. We express the results of the significance test in terms of a probability that measures how well the data and the claim agree. To see how you conduct a test of significance, consider this simple example. Suppose a basketball player claimed to be 80% free throw shooter. To test his claim, we have him attempt 50 free throws, and he makes 32 of them. His sample proportion of made shots is 32 over 50, or 0.64. What can we conclude about the claim based on this sample data? So in this case, we have an hypothesis about the population parameter, in particular that a basketball player shooting hoops can score 80% of the time. We want to check using a sample of 50 shots if this claim is true. So how can we do this? Well, we would look at the distribution of the sample mean. And we would then look at how likely it is to get a sample where the average score is just 0.62. You score 62% of the time. To get an idea of the distribution of the sample mean, let us simulate 400 samples, each one of size 50. Then we will try to determine how likely it is that in 50 throws he will score 32, if he really is able to score 80% in the long run. You can see from the graph that from our simulations that the likelihood that he will score only 32 out of 50 of these throws is very small. Therefore, it is very unlikely that the actual population parameter is 0.80, that he is able to score 80% of the time. And there are two possible explanations. Either we observe something very unusual, very unlikely, or the player's claim is untrue. He actually cannot score 80% of the time. Because this probability is so small, we prefer the second explanation. Therefore, in statistics, we would say that the data gives convincing evidence that the player's claim is not true. Basically, we are saying that we reject the hypothesis based on the data. A test of significance starts with a statement with regards to what you want to test using your sample data. So this statement actually involves two parts. One is a statement of the null hypothesis. This null hypothesis is often a statement of no effect or no difference in the true means. Your test is designed to strengthen the evidence against the null hypothesis. This is a very important section to understand hypothesis testing or tests of significance. All the significant statements that you get from hypothesis testing is when you reject the null hypothesis. So you want to see if the data contradicts the null hypothesis. In this case, the result you'll see later, the result of your test will be to reject the null hypothesis. If your data does not contradict the null hypothesis, then it doesn't mean that the null hypothesis is true, it just means that there's no evidence against it. So remember that when you state the null hypothesis, you are always trying to find data that contradicts this null hypothesis, and that will be a very strong statement. The data that confirms the null hypothesis makes a weaker statement of, well, there's nothing to contradict this statement. So in the example that we saw before, the null hypothesis was the probability of scoring in a free throw was 80%. The second part of your claim is going to be the alternative hypothesis. This is actually the hypothesis, the claim for which you are trying to find evidence for. This alternative hypothesis can be one-sided, in which case you are trying to figure out if a parameter is larger or smaller than what's in the null hypothesis, or two-sided if you want the parameter to be different from what is stated in the null hypothesis. So in the previous example, your alternative hypothesis was the probability that is different from 80%. To see how you set a hypothesis test, consider this example. So one study shows 18 subjects at random from a company with over 200 workers. Half of the workers were assigned at random to each of the two groups, but both groups did similar assembly work. One group, however, was allowed to pace themselves, while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 more weeks. The response variable is the difference in satisfaction scores, self-paced minus machine-paced. So let us think, how would you state the appropriate hypothesis for performing a significance test? The population parameter for which we have information is the population mean mu of the difference in job satisfactions, self-paced minus machine-paced, in the population of all assembly line workers in the company. What you want to find out is if it is different. So you would set your null hypothesis as there's no difference, and you would set your alternative hypothesis as being that the job satisfaction is different between the two types of jobs. Try now the following multiple choice questions. The correct answer is, the null hypothesis is the average mu greater or equal to 450 pounds, and the alternative hypothesis is mu smaller than 450 pounds. In this case, you want to dispute the claim that earnings are 450 pounds or more, which implies that you want to reject the idea that the average earnings are 450 pounds or more. Therefore, you need to set this as the null hypothesis. If you reject the null hypothesis, then the alternative is true, which is to say that the average earnings are below 450 pounds. Also remember that the null hypothesis always has the equal sign. The correct answer is null hypothesis that the average mu smaller or equal to 299 hours. Alternative hypothesis is that the average mu is greater than 299 hours. In this case, you want to show that the batteries last more than 299 hours, which implies you want to reject the idea that they last 299 hours or less. So your null hypothesis is that the average life of batteries is 299 hours or less, so that if you reject it, you will show that the average life of these batteries is 299 hours or more. Also remember that the null hypothesis always has the equal sign. The correct answer is null hypothesis that the average mu is smaller or equal to than 1.75 kilograms, and the alternative hypothesis is that mu, the average, is greater than 1.75 kilograms. In this case, you are concerned that packages have a weight of more than 1.75 kilograms, which would increase costs to the firms. Therefore, if you reject the idea that the average weight of packages is 1.75 kilograms or less, then you have a problem. So your null hypothesis is then that the packages are 1.75 kilograms or less, and if you reject it, you know that you have a problem to solve. Again, remember that the null hypothesis always has the equal sign. And this concludes our lecture for this week. We talked about confidence intervals, how to build them, and what do they mean, and we talked about hypothesis testing. We started talking about how to build a test of hypothesis. Now, to review, consider the following question. Suppose you take a sample and make a confidence interval. What is the implication of the mean from a new sample not falling inside the original confidence interval? Consider this.